Hello everyone, I'm Xiao Gang. We'll continue next. To make it easier for everyone to follow, let's still mark this thread to avoid any issues. This should be the audio thread. The audio thread streams data over, executes on the audio thread. Okay, alright, that should be about it, no problem. Then on this audio thread, we need to do some work. This time, the work is more complex. First of all, because it's an unstable stream. The streamed data might be abnormal, or it could be equal to 0. That is, if you want to check how much data it has actually streamed, you can extract this code for everyone. This is my debug code. That is, we can retrieve this information here and then let it print a log on the main thread. Check what the device is called, how many channels it streamed. It streamed some sample rate information of the device. This is the debug code. I'll comment it out for everyone. It's simple. We need to include these logs here. Let's include all the same files because we'll need them later. First, we need to include this genuity thing. This is related to audio. Then we include the test graph related ones because you'll need them for debugging. Then we'll use the Kismet related ones. And this instance 3 might also be mainly this log. Okay, the log. Let's copy this log as well. It should be this file. Okay, our specific log. It's actually this one. Okay, for now we'll use these. We'll add more when we need them later. Let me replace this Japanese asset for everyone. Okay, this comment. Anyway, take a look. Follow along and make the changes. It should be fine. Okay, so here. Anyway, it's on the audio thread. The whole thing is executed on the audio thread. If the data sent out is incorrect, we'll skip it. We'll just ignore it. And then, actually, we still have one more step here to calculate the audio volume. We'll control it up to here. To do, okay, we'll ignore this for now. Then in this part, we may use a method to append this data. Why do we need to write a separate method to append data here? It's because we want to add a lock, but I don't want to place the lock here. I want to write a separate method because, like this open data, ET is actually placed together with our course atata are placed together. So I took this part and wrote a separate method for it. Okay, this method appends data. So this is very simple. Just add a lock. Then here we take this data and add it in using the opens approach. Directly add this segment of data into our data. Okay, there shouldn't be any issues here. Okay, so after you have appended data, you definitely need to retrieve data. If you do not retrieve this data and do not consume this data, then this data will keep accumulating. And this will lead to a problem, which we often call a memory overflow. So let's prepare another piece of data. Then retrieve the data and retrieve it in this way. But when you retrieve it, it may not always succeed. Why is that? Because when you retrieve it, you must retrieve 640 sample points. So it may not always succeed. Let's write this comment here, right here. We must retrieve 640 sample points at a time. Only then do we consider it successful. We definitely need to add a lock first. Then add a lock. We must clear this data. At this point, we need to make a judgment. Because the data flowing in from here could be 48 kHz dual channel, or it could be some other required format. So we need to perform resampling. So how do we do this resampling? Actually, it's relatively simple. Let's first write the first type of resampling. The first type of resampling is the simplest one. Well, this involves a bit of mathematical transformation. That is, if it is 48 kHz dual channel, or a single channel, or 16K dual channel, or 16K single channel. Obviously, if we have 16K dual channel or 60K single channel, we can directly take 644 pieces of this data and put them in. If it's 48K, then we need to take every other 2 data points, right? If it's dual channel, we need to multiply by 2. That is 48K dual channel requires taking every 6. And 16K dual channel requires taking every 2. 48K single channel requires taking every 3 points. You can understand it as, and for 16K single channel, we can input it directly. So how do we write this here? That is how to write it, because we are writing this together. So we do it this way. To write such a process, we multiply the number of channels by its sample rate, then divide it by this capture sample rate, the coefficient we want to capture. So obviously if this is 1%, then this coefficient here must be 1, right? The maximum value of this coefficient might be 6. That's the situation. And this is the number of points we need to sample at one time, right? Okay. So this is the number of points we need to process at one time. If its coefficient is 6 times, so you might be equivalent to 1 time, you would need 640 points. So you would need to process a total of 3,840 points. It should be like this. I should ask if everyone understands this part. Let's draw a diagram for everyone. We'll draw this diagram now, okay? Let's draw the diagram first here, because this part is very important. So I want to emphasize it. So we agree that the data we need is 16K by 16K, right? And it's single channel. We call it single channel. So the data we need. So we use A, we use L and R to represent our single channel. We can understand this data as L1, L2, L3, L4, L5. Okay, this is our single channel data. So if this is the data we want to send, if we have dual channel data, how should we do it? Right, obviously this is not single, it's dual. Okay, so actually we have L1, E, LR, R, L3, R3, L2, RC, L1. So obviously, we essentially only take one side. So actually, we need to process 640 points here. And here, there are actually 1,280 points, right? Yeah, we only take the points on the left side, or only take the points on the right side. So this is where we handle it. As for our coefficient, it is essentially taken like this, skipping 1. Then here comes our question. We are at 48K, right? If we have a 48K channel, then for this part, let's use A. Let's use A to represent it. Then let's still use L. Still U. So this is L1. Then in between, there is actually another one, which we call, there will be 2 extra points in the middle, right? Then we call it L1A. Then L1B. These 2 pieces of data are not needed. The next is L2. LRA. LRB. Then next is L3, right? L3A. L3B. So obviously, it's sampling. The number of sampling points is 3 times the previous one. 3 times should be 1920. Right. So what data do we need exactly? Anyway, we do need this data. We also need this data. Right. We also need this data. Okay. So obviously, this LEA, we don't need LEB. So this is 1920. Then if we have a dual channel at 48K, a dual channel at 48K. So obviously, this way we have LE, okay, lab, and this side is R. This side is, let me check, this side is R21, okay. This side is R1A, RB, and this side we have L2, LRA, L2B, and this side is R2, R2A, R2B. So obviously, the data we need is this. Okay, so obviously on our end, we need to process a total of 3,820 sample points. In this case, for different audio input devices, the data we need to resample is different. But we need to ensure that after resampling So this is what I wanted to explain to you. You should understand this now. So obviously for our first case, its coefficient is 1. For the second case, its coefficient is 2. Corresponding to the third case, its coefficient is 3. Then for the last case, its coefficient is 6. Okay. So let's stop here for this diagram. Everyone can take another look and try to understand this diagram again. That is how exactly this is done. Okay, let's minimize this thing here. Minimize. So obviously this coefficient is the coefficient between the number of channels and the sampling frequency. So this coefficient is 1, 2, 3, 6, right? Right. If so, then this place is the number of sample points we need to process at one time. Everyone, take a look at this diagram again. 1, 2, 3, 6. Okay, no problem, right? Good. Then after this, we need to make a judgment if all of the current data is greater than the number of sample points we need to process at one time. Then it proves that this time we can resample it because it meets our requirement. Then it's very simple. We will iterate once the number of samples to resample. Then we are iterating over this. This is 640, which is equivalent to we need to prepare 640 sampling points. The number of points between each interval is our A6 fix. Then here we do extract from this number from our original data. Extract after correction according to the required coefficient. Put it into the number we need to output. After this extraction process, let's go ahead and let's remove these resampled ones. These 640 or 1280 or 1920 or 3820. Because this batch of data has already been resampled. We've already resampled 640 data points, so that's fine for us. Okay, so after the resampling is done, we can then return a false for it. And right here, we will return a false to prove that we have resampled the data and put it back. Right, actually, we have another issue here. That is, if it also has a common frequency, because it might be this frequency, can we use the same method to resample it again? Unfortunately, I have to tell you that you cannot do this, because this cannot be found. This is what we call a common multiple, or something like a common divisor. So we will control it here for now. We can add it later for you. But for now, let's just write it together. If it is neither of the format, actually at this point, we will let it crash. This means there is a major problem with our audio device. It is not a common audio device. For example, if it suddenly shows a time-space channel, then obviously we cannot handle it, right? Then we need to remodify the encoding. Let's explain it to him first. If it's this 44100 method, how we should handle it. Actually, the way to handle it is relatively simple. Let's first explain the principle, then everyone will understand. Okay, alright. It was originally like this. Let's bring up the comparison. For example, here, let's take this, still using 6K, Shiluke single channel. Right, then our sampling points are like this. We call it 1, 2, 3, 4, 5, 6, 7, 8, 9. For example, if we only need 10 points, but if it's this 44.1K, this kind of sampling frequency, we'll take this single channel as the standard. Then its distribution, then it might not be distributed like before. It might be this kind of molecule. It is 1, then A, then 1B. Then here it actually isn't called 2 anymore. Actually, let's not use that. Cannot use it here. So their starting point, the starting point should definitely be the same. So it's this long segment. It has 10 points. And then in here, actually, this segment of ours, actually we don't know. This segment is also this long a period of time, but exactly how many points does it have? Actually, you can divide it, because this should be it. Let's take a calculator and divide it for everyone. We divide 44.1 by 16. You'll find it doesn't divide evenly, right? Our 27 is equivalent to. There are about 27 points here. It should be 27 points. So actually we use the symbol. That is A, B, C, D, E, F, G, H, I, J, K. There are 27 points here. You need to redistribute them to these points. So actually this part is somewhat similar to this kind of linear interpolation method. You take this value here, then interpolate it, and then take point A, point 2, and interpolate them out like this. For example, point 1. This point 1 is definitely the same as point A. They have the same starting point. Then this point 2 is between C and D. Then based on this position, it is between C and D. Then you take a value for CD. For example, point 3. If it is between F, G, and G, then you see whether it leans toward F or toward G. Then you, for example, if it leans toward F, if it leans toward F, or if it leans toward G. It depends on which contribution has a greater weight. Then you can think UA essentially F plus 0.3 times G minus F. That's basically what it means. Get it? This is linear interpolation. If you're not quite clear on it, keep looking at it. It involves the professional green wave. That is how to sample this thing. Okay, let's just write it down here. We'll do it like this. That's roughly what it means. Okay, everyone should understand. I'm just saying. Anyway, you need to take the 27 points, resample to 10 points, then work on this segment of time data. Okay, now let's take a look at how the code is written. First of all, we still need to handle how many sample points we need to process at once. Such sample points. So here it is, this 16K, 16K. Then multiply this by the number of channels to calculate the coefficient for the sample points. What does this mean? This is equivalent to how many we need to process every 40 milliseconds. So 41. That means every 40 milliseconds, how many raw 900 sample points of data. That's what it means. Sample point data. Obviously, then we take 100. We just divide by 25. So every 40 milliseconds, we need to process 1,764 points of sample point data. And if it's 16,000, we divide by 25. So it's 6,200. So we need to take the 1,764 points and resample them to 640. Then let's write the comments for everyone. For the single channel here, it's essentially taking the 1,074 points and sampling them into 640 points, right? So how is this 25 derived? Because it's 40 milliseconds. It chooses milliseconds. That is 1,000 divided by 40. So this 25 is actually equal to 1,000 divided by 40 milliseconds. Let's write it down for everyone. 80 milliseconds divided by 40 milliseconds. Okay, let's just leave it at that for this part. That is for every 40 milliseconds. How many sample data points we need to process? So here, multiplying by this has to account for the dual channel. So there is a step coefficient here. We'll just ignore it. If our current data already meets the requirement for us to process it, then here, we extract these current 64 points. So the horizontal axis here is these 64 points. And then we have a step coefficient here, right? This has a step coefficient. If you know this part, it's mainly about me handling dual channel. You just need to understand single channel first. Then, based on the point we want to achieve, right? We select the step size for it, right? Here, this index. And then finally select it. If it's single channel, you add 1 each time. If it's dual channel, you add 2. Then here, 64 points are selected. After selecting them, we need to perform resampling on this data. So we have a method here called resampling. This is our original data. Then we resample it into 6,040 data points. Finally, we remove these $34 data points from our original dataset. At this point, we consider the sampling to be successful. Next, let's write the resampling algorithm. Whether this algorithm, I'm not sure. I can't guarantee this algorithm is correct because on my end, I just wrote it roughly because I think you adapting to multiple things might as well just change the audio devices. But I mean, okay, so obviously here we prepare a host for our output. because we are outputting through this, right? We shouldn't modify it in this position because we don't really want it to output in its original position. This would make our thinking process quite confusing. We can't change it. And this is this resampling. Ratio, you can see a ratio, and then here we use a negative loop. Then we perform a recursive judgment. So then it's not a recursive judgment. This is a linear interpolation. How is it interpolated? Actually, this is my interpolation method. That is, if this 2 is between C and D, then it interpolates according to the positions of C and D. Do a linear interpolation. After interpolation, we just return this data. Okay, alright, this may not necessarily be correct. It's just to show you the idea and direction. There is a resampling linear brush here, an algorithm in here, but the engine's underlying system also has resampling. If you study the underlying audio module, especially when it comes to pixel streaming audio processing, we wrote all of this ourselves. We don't have a method to directly remove the engine. And this part is mainly to introduce this concept to you. So after doing this, then come back here. Let's go back to where it is called, back here. At this point, we have actually already handled it, okay? Of course, if this data does not meet the requirements, it means this sampling attempt has failed. Failure is very normal because you only sample every 40 milliseconds, only save once. Only then will it be enough to save the next and more because your audio data accumulates over time. Then the frequency we take must be slightly faster than your accumulation frequency, otherwise you won't be able to keep up. If your consumption speed cannot keep up, it will keep accumulating here. So in this case, if it's not enough, that's fine. We can just let it succeed the next time it comes to fetch. So we have written this part for you. We can compile it. It should pass now. And basically this audio part's already written. We haven't added a calculation for audio size yet. Let's ignore this for now. Then you can test it somewhere. Then set a predictable E. You can take a look at this, see if it is continuously accumulating here. So that's all for this lesson.